Hey guys, thank you so much for joining in on this live session on hands-on machine learning workshop. And today we'll be looking into the chapter number 4 as part of our discussion today. So folks, can I get a quick confirmation whether you are able to hear my voice and see my screen? Can you please confirm? So folks, please confirm whether you are able to hear my voice and see my screen. So please use the chat window if you've joined through the social media platform. Ensure that you respond over there so that we'll have a confirmation before we get started, guys. Okay, so thank you, Dheeraj. Thank you, Lakshmikant. Thank you, Ramesh. Thank you, Kavya. Thank you, Sridhar. Okay, I see confirmations. Thank you so much, guys, for confirming. So, folks, I hope you're all doing good, and I hope you had a chance to proceed with your learning journey. In the last week, we have actually looked into the chapter number 3 in our discussion, and I hope that discussion was helpful to you. Now, I want to take a quick pause and ask to you guys, do you have any questions in general related to the machine learning, deep learning? So please feel free to let me know before we get started with today's agenda. So Rakshit says, sir, I couldn't progress, but I hope the summary would help me. Okay, that's fine, Rakshit. Okay. How about others? So any questions? Okay. So Raghu says, I'm not sure what to do after learning generative AI. So, Raghu, so the that's a very good question, and that's, I would say, a valid question, I would say. So if you have learned the generative AI, so just want to get some more perspective. So are you talking about learning from the Manifold AI learning course of generative AI or generative AI in general? Can you please let me know so that I can explain with some more context? In general, okay, that's a good one. So here, when we talk about after learning the generative AI, so one easier way is, or one the best way, which everyone is looking at, most of the companies are looking at right now, is how you can use that generative AI model and perform the fine tuning and deploy it as part of their company product. To give you a perspective, if you consider the example of ChatGPT. So if you consider the example of ChatGPT, here in this ChatGPT, you would go ahead and ask the question, and this is a general model, and it is able to give you a response on the knowledge that it has been trained on. For example, if I say, uh, what is transformers? Like any general question, if I ask, this model is able to answer me. But suppose you are working in a company and maybe the name of the company is TCS. Now if you ask the question as what is the leave policy in my TCS? So here it says that this language model do not have the information about your company policy. Overall, what I'm trying to say is the models that are available right now, the generative AI models, it has been trained on general data. So I would recommend you find a way to fine tune such model, fine tune these generative AI model and deploy it uh, in the production environment. You can make use of the knowledge that you have gained throughout our learning that is on the webinar series. If you have checked the live sessions that we have conducted earlier, there are multiple sessions that we have conducted around the ML ops and LLM ops, how to deploy the machine learning models, how to deploy these chat GPT model into the production environment. You can make use of those sessions that you have attended, and by referring those sessions you can actually gain more perspective as how you can deploy such a generative AI models to the production environment. So that should be the next step, Raghu. Okay, anyone else has any other questions, team? And thank you, Raghu, for asking that question. Okay, so team, if you are good to start with today's agenda, please confirm by typing as good to start so that we'll get started with today's agenda and we'll continue with our discussion. Okay, Rakshit, Ramya, Diksha, Raghu, Samiksha, Narayan, Lakshmikant, Sridhar. Okay, Rishabh says that's his first session. Okay, no worries, Rishabh. I'll start with the agenda when we start this today's session. Okay, Ramya. Okay, thank you so much, guys, for confirming. So let's proceed ahead with today's agenda, guys. So before we proceed ahead with today's agenda, so this session is made possible with the team of Manifold AI Learning. So I just want to let you know about the Manifold AI Learning. Manifold AI Learning is a learning platform where you can learn the topics like generative AI, ML ops, LLM ops, Python, MLOps with AWS, mathematics for machine learning. So there are various courses that have been created by Manifold AI Learning, which me as an author got an opportunity to create with them. And one such course that we have got is the Complete MLOps Bootcamp. I highly recommend you to check out this course if you're someone who wants to take your learning journey further to the next level. And this course is available on the marketplaces like Udemy. So it's one of the highest rated course in the topic of MLOps. So you can learn from Udemy or you can learn from Manifold AI Learning website. So where you can get the best deal. And this course is being referred by more than 20,000 learners, like 1,000, more than 1,000 learners from Udemy Marketplace and more than 20,000 learners to the Manifold AI Learning platform. So professionals all around the world are liking this course and we want you to make the best use of this course, and we are currently running the deal on Manifold AI Learning site, and I can also share you the coupon code on Udemy as well. So feel free to check out the course link and I look forward to seeing you on the session on these courses. This has got more than I'll say 39 hours of video content which talks about in depth about each and every topic, which is about how to work with Python, GitHub, working with the ML file, packaging the models, how to create a package, ML flow, Docker, so Streamlit, how to deploy using Flask, Linux operating system, Jenkins, monitor and debugging the ML system, Prometheus, Grafana, Docker Compose, and what to do after productionalizing the machine learning model. So you will be learning end to end from this topic of machine learning operation in depth, guys. Okay, so that's the best part. So I've shared you the link of both the pages. One is from Udemy platform and the another link is from the Manifold AI Learning site. I highly recommend you to check out the same and I look forward to seeing you on the course. And if you buy from the Manifold AI Learning platform, they can also make use of the coupon code YouTube to avail 20% off on the prices that you see on the page. Okay, I look forward to seeing you on the session, guys. And I got an opportunity to create with them, and you can also check out the other courses from them as well. Okay, now coming back to our learning journey. So here, as we progress in today's session, we will be into the chapter number 4, which is the hands-on machine learning. Now, when I say chapter number 4, the overall agenda of this session is will take you through the concept of linear models. So this chapter is about the linear models and we will be discussing about the gradient descent, the different types of gradient descent, batch gradient descent, stochastic gradient descent, and mini batch gradient descent. And we'll also talk about the regularized model, and we'll also talk about the logistic models. Okay, that is logistic regression. So these are the topics that are part of this chapter number 4. And we'll be discussing about all these as we progress in this session. Okay, I'll summarize and I will give you an intuition behind these models so that you get a understanding as how it actually works. So let's get started, guys, and let's start with the chapter number 4, that is training models. Now, just like we did in the last session, I would go ahead and load the GitHub repository of this book. And since we are now in the chapter number 3, I'll just chapter number 4, I'll just bring up the training linear models. In the parallel, I've got my notebook open so that I can give you a perspective as what is happening over here. Okay, so even though you may not have covered the notebook, or you may have, even if you have joined for the first session, that's still fine, because what you're learning today, it's core machine learning. So it's a core machine learning. The benefit is we already have a already created notebook which you can refer it for free. So that's a benefit, guys. Okay. All right. So with that being said, so let's proceed ahead. So when we talk about this chapter number 4, it's about training the machine learning models. So when we talk about training the machine learning models, it's about learning the pattern in the given data set. Now, what happens in the machine learning model is, so we will instantiate the model. It can be linear regression model or any model, and we will say model.fit, and we will specify the data set, that is X and Y. So X is nothing but the features, and Y over here is nothing but the target. So when I say model.fit X comma Y, we are interested in learning the pattern between this X and Y. Now today's discussion is about how does linear model would work when I say model.fit X comma Y. Now to start with, the first model that we have got is called as a linear regression. Okay, I think okay. I'm okay. So I hope you're able to see my screen. Thank you, Raghu, for sharing. Okay, yeah, I was actually sharing. I think it was visible only on the one side. Okay, all right, folks. So the topic that we are going to learn is the linear regression. Okay, that's the model that we are going to learn right now. Now, when we talk about the linear regression, so here what it means is we are trying to find the relationship between input and output, and we are expecting there is a linear relationship between them. Now, when I say linear relationship between my input and output, it would mean that, okay, it would mean that there is like this X and Y relationship can be expressed in terms of a straight line kind of an equation. That's what we can say when we mention as we have a linear relationship between them. Like, to put it simply, like if I have a single feature and if I have a target Y, okay, the relationship between this X and Y can be established as Y is equal to mx plus c. So that's the core idea of this linear relationship of the linear regression model. Okay, so that's the overall idea right here, team. Now with this basic in place, if I want to go ahead and generalize this model to the multiple features, then we will say y is equal to theta naught plus theta 1 x1 plus theta 2 x2 up to theta n xn. Okay, so this is how we will describe the relationship between multiple features of X with my Y. So that's the core intuition that you need to have. So here X1, X2, X3 up to Xn. So all these are the features. X1, X2, X3 up to Xn are the features. Theta naught, we call it as the intercept, and theta 1, theta 2 up to theta n are called as the coefficients. So this is the basic that you need to remember when we talk about the linear regression model. Okay, that's the basic that you need to remember when we talk about this linear regression model. Now, with this basic in place, now let's proceed ahead and try to understand about it. Now, once we have established, okay, this is how the model would look like. Now, obviously, we also require a way to establish the relationship between this x and y. Like when I say establishing the relationship between this x and y, so here we will be sorry, like when we say after we establish relationship, to check whether the model is working as per our expectation or not, we need a way to evaluate the model. So this y is equal to theta naught up to theta and xn, like that's actually the relationship between x and y. Then once we have learned that relationship, to understand how well we have captured the relationship between x and y, so at that time, so what we do is we make use of the evaluation functions. So if you remember in the previous live session, we have seen the various evaluation functions for the classification. Now we would go ahead and look into the evaluation functions for the regression as we progress in this session. Now, one important thing maybe that I can highlight now itself is the evaluation function. When we talk about regression, is basically one of the most common one is called as the MSE, which is nothing but the mean squared error. Now, when I say mean squared error, it's basically the difference between my uh, given output minus the predicted output, and we'll take a square between them, and I'll divide it by n, which is number of data points. Okay, so here I'm taking the mean of squared error. So this y minus y prime is basically the error. So since I'm taking this error square and dividing by n, so we'll call this equation evaluation function as the mean squared error equation. Now to find the values of theta naught, theta 1, up to theta n, to find these values of these coefficients, there are various ways of doing it. So one mathematical way is called as the normal equation method. Now when I say normal equation method, this is given by, so theta hat is equal to x transpose x whole inverse multiplied with x transpose y. So by applying this equation, I'll be able to find all the values of theta. This is called as the normal equation method, and that is what is described in the initial part of this learning journey. So we have considered some data points. See, we have this x1 and y. So just for simplicity, we have considered a single feature, and this single feature is having a relationship with the target. So we have the single feature and the target, and with this single feature target relationship that we have, now we are trying to establish a relationship. So first thing that we did is, so we have applied the same normal equation, which is nothing but inverse of x transpose times b, that is x, okay, and multiplied with x transpose times y. Okay, that's something that we have added. And before we added this, we have added a dummy feature. Now this dummy feature needs to be added because when I'm performing this normal equation, so at that time the system does not have the capability, to determine the bias term, and that is the reason that we have to determine it in this manner. That means we have to add this dummy variable in this manner, team. Okay, so once this is done, so if you simply look into the equation, like if we compute it, so we'll get the output as theta best is this. Okay, so and once we have these values of theta, so values of theta best, if I have a single feature, is nothing but values of em and b, that is the coefficient and the bias term. Once you have it, so if you have any new data, you can send in the new data with these values of coefficients, and you can predict the output. Like here in this example, if I have 0 and 2, the respective output will be 4.21 and 9.755. Now we can try to visualize it. So what we were able to do is we were able to draw a straight line which passes through most of the data points. And that's what fitting of any model is. Now I've got a question for you. Okay. Now I have a question for you as why do you think that we need to fit a model for a given data? So what is your understanding in general as why do we have to perform the fit for a given data set? What benefit are we going to get? So can you answer, team? So what benefit am I going to get if I perform the fit of my machine learning model? Okay, Raghu says not sure. Okay, Rajiv says it will help me to generalize. Okay, Rakshit says I can generate the prediction. Soumya says I can find the output. Okay, that's correct, guys. So, as most of you have mentioned, see, the reason that I want to fit a model because here with my model, I'm able to express with the help of a straight line, which is of the format y is equal to so 9.75x plus 4.21. Okay, this is what the equation of the relationship between this x and y would look like. That's the equation of the straight line. So if I do not have this equation, without this equation, if I have to describe my overall data point, then at that time I'll have to specify and I'll have to mention each and every data point over there. So obviously I'll have to share the data if I want to share that information to any other person. And another thing is, if I have that information, it is just the existing information to me. If I have another value of x, well, let's say if my x1 is equal to 3, with this x1 is equal to 3, I'll not be able to predict what would be the next output of y, that is its respective output for the given x. So one, it will help me to understand the existing pattern in the data and compress it and represent it in a generalized manner so that we will be removing all our details that we have got. And another advantage is once we have established that relationship, we can generate the output for the new data. Okay, that's the idea. Okay, that's the idea of importance of this fitting the model. And Raghu says close to accurate data. That's correct. So what we have built the model, it's the best possible model for the given data. Okay, so we are able to build the same. Now what we had implemented is a normal equation. Now if I want to implement the same using the scikit-learn library, so I have imported the model, that is from sklearn.linear underscore model, import linear regression. Then we have instantiated the model. And once we have instantiated the model, we have performed the fit for a given data set. And once the fit is done, we are generating the prediction. Okay, okay, once the fit is done, okay, we are trying to display the intercept and the coefficient value. It's almost the same like what we had got earlier, 2.77 and 4.21. 4.21, 2.77. So we are able to see the same output like we had earlier. Now we can generate the output as well. Like predict, after we call the predict function, we are able to generate the output. Okay, so that's the overall idea right here, team. Now, if I want to go ahead and uh, like if I want to get the linear regression over here using the SciPy library, we can also do that as well by calling the np.linearalgebra.lstsq, that is least squares method. Okay, it's another method that we have got. So this technique is called as the uh, uh, technique which is based on the normal equation, which follows the least squares method. Now, apart from this technique, there's another technique that's called as a gradient descent technique. Now, here, when we say gradient descent technique, this is another technique that we have got. in fitting the model for a given data set. Now, what happens in the case of this gradient descent technique is, in this gradient descent technique, we will initialize the values of the parameters to a random place or to a random position. Then we will make use of the gradients to decide in which direction that we have to update the parameters such that the value of loss, in this scenario, the squared error loss will be minimized. So that's the intuition behind this gradient descent technique. So here what we have done is we have created the equation which we have found for gradients. So here when I say gradient, it's basically derivative of the values of my derivatives of my values of my derivatives of my loss function with reference to my parameters. It can be del L by del X, del M, or del L by del B, assuming M and B are the parameters, or theta naught and theta 1. So it can be anything. So that's how we would go ahead and find the values of the gradients. Okay, we would go ahead and find the values of the gradients, and once we find the values of the gradients, we will update the values of the gradients such that we will update the values of the parameters. So think of it in this way. Okay, so let's assume that, okay, you have a required equation which is of the format y is equal to 2x plus 3. This is the required solution. Now here in this case, m is equal to 2, c is equal to 3 if I consider the equation as y is equal to mx plus c. Now, let's assume you would consider your m as 0.5 and c as minus 1, or let me make it as c as plus 7. Okay, let us assume this is the scenario. Now, if you use this value, okay, so by comparing it to the existing value, you know that you have to increase the value of m and you have to decrease the value of c. So the way we will be doing it is we'll be finding the values of my loss function, which is nothing but the mean squared error, which you have seen earlier, that is y minus y pred whole square, I can say y hat whole square divided by n. I'll take the loss function as this, and I'll take the derivative of my loss function with reference to m as well as c, and I'll be updating the values of m such that m is equal to m minus eta times del L by del m, and c is equal to c minus eta times del L by del c. So this is called as a gradient based technique of updating of the parameters. This derivative is called as a gradient, and the same has been implemented over here in this formula. In each and every epoch, we would go ahead and find the value of loss, and once we find the value of loss, we would then go ahead and take the values of this gradient, and will after we find the gradient, this is how we'll be updating the values of our parameters. So this equation that you see right here, so if I actually calculate the values of the gradients, this is how the calculation would look like. You can check out, there's one more video that has been created in the Manifold AI learning page of YouTube channel. I can share it in the email once the session is completed, where we have actually shown you as how to calculate the gradients, which we have described in detail in one of the video in our YouTube channel. Okay, I'll be sharing it once the session is completed. So this this will be finding the values of the path. This actually takes care of the gradient descent application. And then, so if you look at it, we are just doing this multiple times. And once it is done multiple times, see, this is just a demonstration. Okay, so how does the learning would look like? So eta is nothing but the learning rate. So learning rate is nothing but the step size. So think of it in this way. Okay. So let's assume that this is your home and this is your office. Now, what I have mentioned is you will make up an iterative approach to uh, fine tune the values of the model, isn't it? So think of it in this way. Let's assume that you want to reach the office. Now what you have did is you randomly went in one direction. Now this is a position that you're in. Okay. Now by being in this position, you want to reach the office. Now to reach the office, so there are various ways. Let's assume that you're driving a car. So let's say you'll take it is 10 kilometers from here. Now if you drive in 1 kilometer per hour, okay, to reach the office you'll take 10 hours. But if you drive in 10 kilometer per hour to reach the office, you'll take 1 hour. If you drive in maybe 33 kilometer per hour, maybe you'll reach it in maybe 3 minutes or something like that. Okay. So yeah, if you'll be reaching it in maybe 15 minutes. Okay. So as you can clearly see, the speed of the car determines how fast that you'll be able to reach the office. In the same way, the equation that I described earlier, there was something called as an eta, which is nothing but the learning rate. Now, this learning rate will help us to move towards the right values. If the learning rate is very small, think of it as your car speed is very small, so you'll take more time, right? In the same way, it will take more time to reach to the correct values and it will require more steps. So when the eta is okay, optimum, it will be better. When the eta is very large, so it might miss out on the correct value. So that's how the values of eta would look like. And there is a stochastic gradient descent. So like if I want to describe the gradient descent, okay, so there are actually three types of gradient descent. One is batch, other one is SGD, and the other one is mini batch gradient descent. So these are the types that we have got. Okay, so but before I describe the types, I'll take a quick pause here. So are you clear with this gradient descent technique, team? So please confirm. If you have understood the gradient descent technique, please confirm by typing as all good. If it's not clear, please let me know. So is the gradient descent technique that I've just explained, is it clear to you? Thank you, Dakshani. Thank you, Ramya. Okay, what about others? Were you able to follow the gradient descent technique explanation? Thank you, Ramya. Okay, so thank you, team, for confirming. So, okay, now when we talk about the gradient descent technique, so here the steps that we follow is first we will initialize the values of parameter, then we will say repeat. This will be like a loop. Okay, so here inside the loop I'll find the value of loss and I'll calculate the gradient, then update the parameters. Okay, once I update the values of my parameters, I would go ahead and repeat the same step. Okay, so this is how the loop would work. Now, if I take one row by row, okay, if I take one row each and for each row, I'll find the value of output and I'll find the value of loss, I'll find the gradient and I'll update the parameter for each row. Then I'll pick up the second row, so on and so forth. Then we call the technique as stochastic gradient descent technique. If I use multiple rows at the same time, let's say 8 rows at the same time or 6 rows, 16 rows, 32 rows at the same time, then we call it as mini batch gradient descent. If I consider all the rows at the same time, then we call it as batch gradient descent. If you consider the entire data set at the same time and using the entire data set, you'll find the value of prediction, then you'll find the value of loss, and post that you would go ahead and update the values of the parameter. Then we call that as the batch gradient descent. Okay, so that is the overall techniques that we have when we talk about the gradient descent technique. And if I want to implement this gradient descent technique, so there is a class that is available inside the Scikit-Learn library that's called as the SGD regressor. So using this SGD regressor, we can actually specify how many number of loops iteration that I want to run, then the eta, which is nothing but the learning rate. Then we will specify our data set. Excuse me. Then we will specify our data set, that is, we'll specify our x and y so that we'll perform the fit on the given data set. Okay, this is called as a batch gradient descent technique, and when I say mini batch gradient descent technique, we'll repeat the same thing. So in Python we do not have a inbuilt way of mentioning the like batch gradient descent technique, so that has been implemented from our hand itself. Okay, that's the intuition, guys. And then when I make use of stochastic gradient descent, so since we'll be processing line by line, as you can clearly see in the visualization, it takes more time to reach the correct value. Okay, so that's the idea and the difference between batch gradient descent, mini batch gradient descent, and the stochastic gradient descent. So that's the main difference between them, folks. Okay, now now that this concept is clear, so let's proceed ahead. Now what we have learned is the linear regression model, and we have seen how to establish the linear regression model for a given data set using the normal equation method as well as the scikit-learn method and implementation of the gradient descent method. So these are the techniques that we have learned till now. Now the next technique that we are going to learn is called as the polynomial regression technique. Okay, now in the case of this polynomial regression technique, we are going to have the polynomial terms. So when I say polynomial terms, we will have the terms where the power of the variables is greater than 1. That's when we call it as there's a polynomial relationship for the given data set. So in order for us to demonstrate the same here, we are considering the data points which is in this format. So obviously no matter how you draw the line, you'll not be able to get the straight line relationship for the given data because of how the pattern would look like. So in order to do that, so the pattern that we follow is, first we are going to generate the polynomial features of the required degree. Okay, to give you an intuition, so when I say degree 2 is nothing but x square x, and like this is how we'll say x square and x when I say degree 2. When I say degree 3, it is x square x cube x square x and 1. Okay, so these are all will be the terms when I say generation of the polynomial features. So here I'm performing the transform using the degree 2. Then once we perform the transformation for the existing data, we'll perform the fit on the given data set, and you can see that by changing the degree of the data, by generating additional features with the polynomial terms, we are now able to find the patterns between the input and the output. That's the usage of this polynomial regression. Okay, we'll create the transforms, polynomial transforms for the given data, and then once we create the polynomial transform, we would go ahead and apply the like try to establish relationship between this x and y. Now one of the common practice that we do in implementation of the machine learning is to create everything inside a pipeline. So here we are creating a model pipeline which consists of polynomial features, then followed by the normalization using the standard scalar and the linear regression. So I'm going to create it as a single object. Okay, I think it is being created in a separate, I believe. Okay, I think in future we have created it. I don't think so it has been created here. So in reality, so what you have to do is when you're implementing any polynomial features, yeah, I think it is created here. See? So like here they have created as a make pipeline, which is a pipeline object, which is composed of first generation of features, followed by the application of standard scalar, followed by fitting for the given data. So that's what the polynomial regression is made up of here in this example. Okay, then we have performed the fit for the given data set and we have generated the prediction, and it typically shows you now. This diagram clearly shows you as how does the model has been fit. So red one is the one where it's a linear regression. Obviously, linear regression cannot learn the curve that we have got in the data set. So it is performing the underfit. And the degree 2 line is the one you can see that it follows it. I would say it's a apt fit for the given data. And when you look into the curve with 300 degrees, so you can see that it has performed the overfit for the given data, which means the number of polynomial terms that we want to add it for the given data set, it's a hyperparameter which we have to decide by by trying out the various combination and use the one which is suitable for the given data set. And we also have the learning curve. How does the learning curve would look like? So on the x-axis, we have got the training set size, and as and when we increase the training set size, so we can see the RMSE values is going to it clearly the on the y-axis we've got the RMSE values. It basically describes how the error would look like. Okay, so that's the idea about this polynomial regression. And then we have got the regularized linear models. Now, when I say regularized linear models, it's a kind of a model where we are going to find the pattern in a given data set. And in this model, for the linear model, we have added the additional term, which we also call it as a loss term. That's called as a the regularization term. So we have three types of regularization. One is ridge regression, which is also known as the L1 regression, L1 regularization. In order to implement this L1 regularization, so first we'll import ridge, then we will instantiate the with the values of alpha, and we'll perform the predict and we'll perform the fit for the given data set, and we can get to see how does the overall model would work. Okay, this is called as the ridge regression technique. Okay, so sorry guys, so ridge regression is the L2 regularization. So I just want to correct myself. Ridge is L2 regularizer. So I've just got myself corrected from the book. Ridge is the L2 regularizer. Here, what we are going to add is we are going to add the term in like the coefficient square is what we are going to add it for our value of loss function. So MSE plus theta I square is what we have it for the ridge regression cost function. Okay, and we also have the lasso regression. So this lasso regression is also known as the L1. So here the loss function is given by mean square error term plus theta I, summation of this theta I. Okay, that's what we call it as the lasso regression. And apart from this lasso, we also have the elastic net. So here this is lasso. Apart from lasso, we also have the elastic net, which is the combination of L1 and L2. Okay, we have got the option to choose how much L1 regularizer that we have to apply or how much L2 regularizer that we have to apply. So we can specify it with the help of alpha and L1 ratio. In the same way, in the case of ridge and lasso, if you have observed, while instantiating the model, we have the option to specify the alpha. Okay, so these are the ways in which we can implement the regularization technique for the given data set so that we can actually improve the overall prediction from the model. Then we also have the early stopping technique. So early stopping technique is a technique where we are going to stop the training of the model if the model doesn't improve further after a certain point. Okay, that's called as a early stopping technique. So we have implemented this early stopping technique manually. So generally these techniques will be implementing it when we are working with the deep learning algorithm. So in this case we are applying in our machine learning as well, and we have implemented the same using the Python programming language. That's all. Okay, so that has been implemented. through our code. In case of deep learning frameworks like the TensorFlow or PyTorch, so it's much simpler to implement it. Next, we have got the next model under the linear models relationship, that's called as the logistic regression model. So what we have just learned is we have now learned about how to implement the regression task for a given data set, and we have looked into the linear models. Under this linear models, we have looked into the linear regression and gradient descent based linear regression, and we have looked into the regularization techniques of this linear regression. So I'll take a pause here, folks. Now I want to know from you, do you have any questions or any queries on the discussion we just had? So please let me know, team. Do you have any questions? If you're clear, please confirm by typing as all good. If you have got any question, please let me know. Okay, Kavya, uh, Naveen, Navya, Sridhar, Lakshmi, Sandeepti. Okay, okay, Vijay, Dheeraj. Okay, thank you so much, team, for confirming. Now, apart from this linear regression, so what we have is the logistic regression. And this logistic regression also comes under the linear model. The reason because here on top of the linear relationship between the x and y, okay, so here on top of this relationship between this x and y, okay, so we'll be applying the logistic function. Now by applying the logistic function, we will be scaling the values in the new range of 0 to 1. So that's the idea about this logistic regression model. So let's go ahead and understand about this logistic regression model and see how it actually works. So when we talk about this logistic regression model, so this is how the logistic regression model would look like. Okay, we've got like you can see that it's like an S-shaped model where we have the values are scaled between 0 to 1. Okay, that's a general way of the output would look like when we are talking about this logistic regression model. And here we have considered a data set which is called as the iris data set, where we have four features: sepal length, sepal width, petal length, and petal width. And using these four features, we want to find the relationship with the target variable. Okay, so the target variables that I've got is the labels that's called as setosa, versicolor, and virginica. So I want to classify my given data set to one of these classes. So it's a typical classification. So in order to do the same, we have instantiated the model, perform the fit for the given data set by building a binary classifier. Then we have actually like we have actually looked into the visualization as well. How does the output would look like, the decision boundary would look like. And then this actually describes where does the decision boundary would be present and how we are classifying the examples. Okay, team. So this was about implementing the logistic regression model for performing the activities like the classifier. So that's the core idea about this classification. Now the process that is followed is still the same. Here during the start of the training, we'll initialize the values of the parameters to some random values. Now post that, we'll be applying the gradient descent technique to update the values of my parameters. Okay, so that's the idea right here, team. Now, when we talk about this logistic regression model, we use it for the binary classification. Now, when we are dealing with multi-class classification, that's when you'll be making use of multinomial logistic regression, or we also call it as the softmax regression. So in this scenario, we'll be using the softmax function. Okay, we'll be using the softmax function and we'll try to express the output in terms of a vector, which describes the probability scores. So here, uh, the model is being implemented. We have generated the output and then we have created the prediction. So this output that you see right here, this is how the output of the softmax would look like. What it says is for class 0, it is 0% probability. For class 1, it is 4% probability. For class 2, it is 96% probability. That is how we would read the output from this predict probability. So what we have looked into it as part of this today's session is we have looked into the chapter number 4 of this hands-on machine learning. So folks, uh, with this we have summarized the learnings from this chapter number 4, which is training the models. In the next session, we'll be looking into an interesting topic that's called as the support vector machine and the various concepts around the support vector machines in the next session. So folks, I want to know from you, so uh, whether this level of detail is it okay for you, or do you think that we need to add some more details for the session so that it can be more helpful for you? So what do you think, guys? So is it okay the way that we are progressing? So if you have got any feedback, so please feel free to let me know. We can try to incorporate it in our future sessions. Rakshit, Samyukta, okay, most of you are saying it as yes, all good, sir. Okay. Diksha, Sampriti, Raj, Sharma, Lucky, okay, Chowdhury. Okay, thank you so much, guys, for confirming. Okay, so all right, folks. So with this, we come to the end of this today's session, and tomorrow we are hosting an event on how do you prepare yourself for your AWS certification? That is AWS Machine Learning Specialty Certification. So tomorrow's webinar is about that, to guide the learners on preparing for your AWS Machine Learning Specialty Certification. So in tomorrow's session, I'll talk about how do you work with the SageMaker. So we'll have a demo with SageMaker. The first part is about giving you an overview of this examination. And in the second part, we'll see some hands-on as how we can perform the machine learning on AWS. Okay, that would be the agenda. And also answer any of the queries that you might have in preparation for your AWS certification, machine learning specialty. So anyone can attend the tomorrow session. It's not compulsory that you should be the AWS certified. Any data scientist or a data analyst who is interested to learn about how to perform the machine learning on AWS are welcome to attend, guys. So do check out our Manifold AI learning page for this webinar details, and I look forward to seeing you guys. Let me share the link over here too for tomorrow's session. I've shared you the link directly. Let me do. Okay, let me directly share this link. Okay, I'm directly sharing you the meeting link, guys, in the chat window. So do register yourself for the session for that is for the next upcoming session. Okay, register for the webinar and I'll see you over there. Now, let me share it again. So, as I mentioned, with Manifold AI Learning, I got an opportunity to create the course. So, I highly recommend you to check out our course on MLOps. So, do check out the course from the Manifold AI Learning page. So, complete MLOps bootcamp, which is made available on the Manifold AI Learning site. Okay, and there are other courses as well for someone who is interested in mastering the LLM ops. So I would recommend you to check out this LLM ops with ChatGPT. Someone who wants to master the generative AI, you can check out this package, which is consisting of multiple courses, which is required for you to master the generative AI. So all these courses are made available in the Manifold AI Learning page, and it's also available on the various marketplaces as well. Do check out our courses over there. And if you have got any feedback on any of the courses, so please drop us a message, or you can ask the questions as well in these live sessions. While learning those self-paced content, if you come across any questions, so you are welcome to ask the questions here as well. I'll do my best to answer any of the queries that you might have. Okay, thank you again for joining in on this session, and I look forward to seeing you guys on the next session. Okay, take care, guys. So if you have got any question, please stay on the call, and let me know if you want to unmute you so I can unmute you as well so that you can ask the question in case if you want to speak. Thank you, Lakshmi. Thank you, Soumya. Okay, thanks a lot, everyone, and I'll see you next time.